Welcome to our second pre-lab video this semester for our 1212 lab here at North Georgia. This week's lab, we're going to be taking a look at solutions and solution formation and really talking about what's called solubility for both solids and liquids and for mixing multiple liquids together. So a couple things to kind of keep in mind when we talk about solutions is really just what kind of helps or causes solutions to form or potentially not form when we're mixing two different compounds together. So most people are probably at least a little bit familiar with the term like dissolves like. Probably heard that at some point in time in some science class. What this really refers to is that you need similar types of polarity or similar types of intermolecular forces. Those two things really go hand in hand with each other in order for solutions to form. Now, in terms of why this really happens, it's really all about the energy that's involved. And so if you don't have similar polarities or you don't have similar intermolecular forces between the things you're trying to mix together to make a solution, they're not really going to interact strongly enough to form that solution. And if we kind of break it down into what are the interactions that are really occurring at the molecular level, there's a few different interactions that have to be broken. So for instance, whatever compounds you're trying to mix together, if you have a solute and a solvent as your main solution components, all of your solute molecules, you have to break up a lot of their intermolecular forces between like just the solute molecules with itself. And likewise, you have to break up a lot of solvent molecule interactions with itself. Once those interactions are broken, now you're able to form kind of new interactions between the solute and the solvent. And really, we're looking at kind of the overall energy change in the whole process. And breaking those solute-solute and solvent-solvent interactions ends up taking a lot of energy to do. And for a solution to form, you have to be able to get enough energy back from forming the new solute-solvent interactions to basically kind of balance out the total, or at least be very close to kind of breaking even in order for the solution to actually want to form. Because otherwise, if it takes a bunch of energy to break all of those kind of starting intermolecular forces, and you're not making strong enough new intermolecular forces to kind of get that energy back, there's no energetic reason for that solution to really want to form. And this is something we'll probably go into a little more detail probably in some of the lectures. But that's really kind of the basis of like dissolves like, is we need similar intermolecular forces between our solute and our solvent, because if we don't have that, our new solute-solvent interactions we form are going to be too weak to overcome the energy it took to break all of our solute-solute and solvent-solvent interactions that we initially had. And so that's why that like dissolve like term really works, as it's really related back to the energy. Now, some solubility kind of just terminology that we should probably be aware of pertaining to kind of forming solutions out of different components. If we're making solutions out of a solid solute and trying to put it, say, in like a liquid solvent, typically we'll consider things either soluble or insoluble based on whether that solid dissolves. So if you add a solid to a liquid solvent and it dissolves, we consider that soluble. If it put it in and it just stays completely put together, it's insoluble. You can also do kind of a middle ground. If it looks like it partially dissolves, you can say it's somewhat soluble or partially soluble. That isn't a perfectly fine description. We'll see a little bit later this semester that solubility isn't really just a black and white, like soluble or insoluble. It's more complex than that. And we'll actually kind of put some math to that a little bit later on this semester after we talked about equilibrium some. For liquids, if we're mixing multiple liquids together, so like a liquid solute with a liquid solvent, we have a little bit different terminology, and these are terms maybe you haven't heard from 1211. If two liquids are mixed together and they form a solution, then they're considered to be miscible. And we basically know that things have formed a solution because all of the liquids are going to look like one kind of cohesive solution. If two liquids don't mix, there's going to end up being some kind of separation, kind of like what you see in the image here. You kind of see a layering effect going on in this. There's an actual like two separate layers to the solution or the mixture that you're trying to create. If you get this layering effect, we consider those liquids to be immiscible, and you basically have not formed a solution. So this would be an example, like this image here, would be an example of where our intermolecular forces that we're forming between those two liquids that we're trying to mix together, those interactions are not strong enough to overcome the ones we'd have to break for just the liquids by themselves, so the liquids just stay separated by themselves and don't actually mix together. So things with different intermolecular forces, like things like water and oil, are things you'll typically see kind of behave like this. Now, there is a quantitative part of this lab that does deal with some kind of different concentration calculations. So big things just to kind of refresh from 1211, remembering that most concentrations are typically going to be given in units of molarity. which is going to have units of moles of solute divided by your liters of the whole solution. But there are some other units that sometimes pop up, things like molality or mass percent, which I've given kind of ways to calculate here. You'll probably hear a couple other ones in lecture as well, things like parts per million and stuff like that. Our focus really in this lab is not just on concentration and kind of units of concentration, but really also talking about solubility. But the reason we bring up these concentration units is that solubility is typically expressed in concentration units. More often than not, it's probably going to have units of molarity, but so a lot of times if you look up like solubilities of things online, you'll probably see a lot of them also given in units of grams per 100 milliliters. Because if you're talking about solubility, like if you have units of grams per 100 milliliters, you're just looking at how many grams of that substance are going to dissolve in 100 milliliters or in a 100 milliliter solution. Typically, it's like 100 milliliters of water that you're trying to put it into. But those are kind of some of the common units you'll typically see for solubility. But they are concentration units is kind of one of the big things you probably want to recognize there. Now, as for our experiment that we're actually going to be doing this week, it's going to have 4 main parts. Let's kind of talk about each part here a little bit more in just a second. But we're basically going to be looking at determining an unknown concentration. And that's going to be kind of our main quantitative measure for the experiment, so the actual kind of calculation involved portion. And then the other 3 parts are all much more qualitative. And so what I mean by qualitative, it's mainly just observation-based. So we're going to be looking at solubility of different solids and liquid solvents, miscibility of different liquids trying to mix them together, and then also effective surface area, really on a rate of solubility rather than just solubility itself. So that first part of the experiment, is actually going to involve finding a concentration of potassium chloride, but I would highly advise that when you start this part of the experiment, go ahead and get everything set up and basically heating. And then basically while you're waiting for things to heat, just do the rest of the experiment, like do the other 3 parts. Because it's going to take a long time for your water to just boil off from the steam bath that you have to set up in this part of the experiment. So set this part up and then basically just let it go, and you can come back to it at the end of lab and get your mass measurement because you basically can't overheat this stuff, so it's not going to take any hurt if it sits there too long. This way you can at least be kind of efficient with your time and basically just do those other parts of the experiment while this one is kind of going. So I get this part started first, like I said, come back to it at the end. And the actual order for the different parts of the experiment really doesn't matter because each part's kind of independent of the others. So if you see that a bunch of people are trying to get the chemicals and things to try and do part 2 of the experiment, see if you can get the stuff to do just part 3 so you can make it a little bit easier and you don't have to wait as much to get access to everything because the order here for the different parts of the experiment really doesn't matter. Now, for this first part of the experiment, this is going to have the only kind of like real numerical measurements you're probably making that are important for this experiment. And so you're going to have to make some different mass measurements, some volume measurements, and things like that you want to record. But do make sure that you're using the right sig figs for everything, or as many sig figs as are as appropriate for your different mass and volume measurements, because that will kind of be part of the things you're expected to show in CSE Pub. If you don't give the right decimal places for things, it's going to count things wrong when you try to enter your values. Right. Second part of the experiment is going to look at the solubility of putting different solids into liquids. And really what's going to happen here is that you're just going to take those solids and mix them with liquids, and you really don't need to worry about having exact masses and volumes. I think this is the one thing that sometimes can make this lab take probably twice as long as it really needs to, is people think they have to have the exact masses and the exact volumes the procedure describes. That's really just not necessary. Honestly, as long as you just have enough solid to mix with enough liquid to see if the solid dissolves or not, that's really all you need. The exact amounts aren't really important. You don't need to record them at all for this part of the experiment because it's really just observation-based. We're really just trying to make a qualitative observation of did our solute dissolve or not. And so as a result, like, is the solid soluble in that particular liquid or not? That's the only thing we're really trying to figure out in this part of the experiment. The third part of the experiment is going to take a look at mixing different liquids together to see if they're miscible or not. So we call this miscibility. It's just, do they actually make a solution or do they stay as separate layers? And so again, this is also going to be just qualitative. You do not have to measure exact volumes. Like if you're taking time to get like exactly like 3.00 milliliters or whatever the given volume is that you need of the different liquids to mix, it's just overkill. You just need to mix the liquids together and basically see, like, do they form a solution or do they stay as separate layers when you put them together. Now, for CSE Pub, You will have some questions as far as any of the mixtures that are immiscible, so things that are making those layers. You're going to be asked to identify which liquid's on top, which liquid's on bottom, and how that kind of relates to the density of the liquids that are involved. And so there's a couple different ways to go through and actually test that. Usually the easiest thing to do is just add one of the two liquids in your mixture and see which layer gets bigger. So if you have water and some other liquid that you mixed and they made different layers and did not make a solution, then just add more water and see which layer gets bigger, and that's your water layer. Now you know what's on top and what's on bottom. It's probably the easiest way to usually make that determination. Now, something that can also kind of come up, and this happens a lot when mixing different liquids, is you might not see like a full separation of the liquids, like where you have like a clear line kind of making your two distinct layers. Instead, what you might see is kind of just like these weird wavy lines going through almost the whole solution. We do consider that to still be miscible, and in fact, that is very common when different liquids do get mixed together and do make a solution. We do still consider that a solution. We consider those liquids miscible, but there is still like some kind of weird things that come out of the actual mixing of those liquids that it's not just going to look like a clear clear just water would. So it might have a slightly different look to it. That's okay. And so that's just something else to kind of keep in mind as you're looking at these. We really only consider things to have a very definitive layering effect to them, where you can see two very distinct layers. That's immiscible, and if they don't do that, then we consider it to be miscible. All right, and then the last part of our experiment is going to take a look at surface area. And really, surface area doesn't impact solubility itself. It's actually more the rate of solubility that it's going to impact. Because what's going to happen is as you go to dissolve something, typically it always dissolves at the surface first. So changing the amount of surface area your particular solid has will affect how fast it will dissolve. But it turns out it actually shouldn't really affect how much will dissolve. And that's probably something that's important for this part of the experiment, is that really what you're investigating is rate of solubility, or how fast something dissolves, not the actual amount. Because given enough time, if you add the same masses, like they should all still dissolve, or like the same amount would remain undissolved out of two different combinations of different particle sizes that you're trying to dissolve. And so like in our lab, we're going to use copper sulfate. It's something that's a little bit easier to tell if it's dissolved. It's a nice bright blue color. And so if you're going to have kind of like the normal just kind of size of particles that comes out of the actual container of copper sulfate. And then we all have a mortar and pestle that you can basically grind it up into a really fine powder, and you can kind of compare similar amounts of each to see how long they take to dissolve. Now, again, for this part, if you want to be exact and try to get similar mass as you can, I think that's probably overkill. If you want to have just like kind of rough estimate, like similar amounts on a spatula tip for each of these, and then just see how long they dissolve, that's honestly probably going to be enough to see the trend that we're interested in. Because hopefully we should just see that increased surface area, or the finely ground, like in the mortar and pestle, copper sulfate should dissolve faster than just kind of the normal particle-sized copper sulfate should. All right, that's really all the main things for this week's lab. This week's lab is actually a little bit on the shorter side because it's, like I said, it's very observation-based. And the only part that you're actually doing any calculations with is going to be on the very first part again, where you just have to make sure you get your masses and your volumes and things like that in the right units. And then the lab will walk you through a decent number of kind of different unit calculations and manipulations while answering some of the post-lab questions. But safety-wise, waste-wise, kind of the last couple things here. Most of what we use can't go down a sink, and I'll make sure that all the instructors are reminding people this week as well. But everything basically for this lab is going to be collected for the waste. A lot of the stuff, anything that basically has any of the solvents that aren't water has to be collected. Like that stuff can't go down sinks. And so we will have some waste disposal that will make sure everyone's aware of kind of where our waste containers are and what to do with those. But no real safety concerns with most of these, other than obviously I wouldn't drink or eat really any of the chemicals, which I think is just common sense. But nothing out of the ordinary in terms of kind of being like extraordinary dangerous, or we have to have gloves, or want to take extra caution with things. Like these are pretty standard chemicals that aren't going to be all that harmful, even if you do spill a little bit on yourself. Although that is something that I would still just always suggest take caution with.